Hey guys, how are you? Please feel free to switch on your cameras, and we can start in a little while when everybody's here. Hey Noah, welcome back.
How are you doing?
Good, thanks. All right. I hope you guys are have been working on the data representation quiz. It closes tomorrow. Yeah, and I see that a bunch of you have posted your hexadecimal names. It's really cool. Jaden, you good now? Yeah, a lot of people helped you. I was glad to see that. Very nice. We can start in about 5 or 10, well, let's say 10 minutes, okay? I think people are probably trying to get in now. Until then, if you have any questions, please feel free to ask. And this is your first class, really. This is the first official class, isn't it? Because on Tuesday was an optional class. Yeah. Also, I hope that you guys had a chance to look at the onboarding video where Chaitra was coding, and we went through the process of creating a lab, a program, submitting it to the Quest site and getting results back. That's going to be essential, I think, because a lot of students basically get stuck at the first Quest, which is the easiest. Not because they don't know the material, but because they say, I'm going to put it off because it's a new system. And that's not a good idea. Do you have any other general questions that you'd like me to address before the rest of the students come here and we start class in earnest? No? Yeah. You should, by the way, you shouldn't feel free to be so, I mean, you should feel free to talk. You shouldn't just be quiet. I know it's early in the morning and all for many of you, but you can use this class as an icebreaker. So just feel free to talk. Do you have, how is it going in general so far? Are you guys okay with what you've been able to see in the syllabus, and working through some of the early problems in the data representation quiz? You get an idea of what this course is about. Actually, you get a better idea after you start questing, because then you'll be coding, right? So when you're programming, which is what will constitute the major part of this course. So we are, yeah, go ahead. Someone had a question?
No, I was just saying, I was getting the hang of it. Data representation, the last few parts, like the multiplying, orthicity, adding, that one's kind of getting to me, but I've really gone, I think I've nailed down the binary, octal numbers, and hexadecimal when I remember divide and then multiply the after the decimal point to the 8 or the 16, and that's how I get the remainder. As long as I remember that, then I...
Yeah, that's fantastic. And by the way, you say that as long as I remember that, right? You'll find that in time, in just a few weeks from now, you don't have to remember that. It just comes naturally to you. It's just a question of getting used to it. And because at the end of the day, it doesn't matter what the base is. whether it's 2 or, 2 or 8 or 16 or 27, doesn't matter. Even if it's base 1. Do you know how you can count in base? Can you count in base? Yeah, you can actually count in base. Can anyone tell me what a base 1 system would look like?
Tally marks.
Tally marks, yeah. Who said that? Noah? Yeah. So basically, in base 1, you only have 1 digit, right? You only have 0. You don't even have the 1. So how do you write the number 5? 5 in base 1 is basically 0, 0, 0, 0, 0. Well, actually, it doesn't make total sense, right? Because it has to be tally marks, like Noah said, because 0, 0, 0, 0 is still 0 in our minds. But 1, 1, 1, 1, 1, that's a tally marks. So that is base 1, essentially. Yeah, so it's all the same. Getting used to it is the most important thing, both with data representation and also programming. A lot of people think that programming, you can read about it and understand. No, it's getting used to it. Getting used to it is the most important thing. There's actually a story, I think about, maybe it's an apocryphal story. Einstein and who was the first computer science? One of the von Neumann. Von Neumann was a mathematician, and Einstein wanted to learn. I believe it was tensor calculus in order to develop his general theory of relativity. And at that time, von Neumann was the foremost authority on the subject. So he went to von Neumann and said, "Hey, professor, can you teach me tensor calculus?" And so the story goes that von Neumann taught him everything. And then Einstein said at the end, "Professor, I understand everything you said." No, what is it? Oh yeah, I see what you said works, and I see that what you see works, but I just don't understand it yet. And I think the response that von Neumann gave was, "Young man," apparently Einstein was a young person, but young man, in mathematics, you don't understand things; you only get used to them. So actually, I don't know how true that story is, but it is very true in many of the fields that understanding comes later, after you get used to it. Because when you're getting used to it, your mind is not trying to understand it. It is still trying to get dexterity, whether it's the dexterity of internal neurons in your head processing information, or your fingers. It's dexterity, and all of your conscious attention most of it is focused on getting the feel, getting used to it. But it is only after you get used to it that your mind has the bandwidth to try and understand it. So you say, okay, well, in some very simple tasks where you don't need the dexterity, where your mind can simulate it and try and understand it even before you do it, right? But you have some more sophisticated non-trivial tasks like programming or playing an instrument or things like that, where the dexterity gets in the way. And so you need to get the dexterity out of the way by just getting used to it, doing it repeatedly. And after you can just automate everything, then you can actually look at what you're doing as you're doing it automatically and say, why am I doing this? Okay, why am I doing this? Oh, that's the reason. Okay, and then slowly the understanding dawns on us in many, even I think, does it work that way with algorithms? Yeah, I think even some of the more sophisticated algorithms that you learn, sometimes we learn that, well, if we do this, it works. And we implement the algorithm with a 50% understanding and see it work. And but then the idea is not to stop. Okay, I got it working. Now I can go on to the next one, because you only had a 50% understanding and got it to work. But the idea there is to okay, I've got it to work now. Now I've got my own thing that works. Let me try and see how it actually works. Let me try and understand it by taking my thing and changing things in there and seeing if it breaks. Change here. It doesn't break. Why does it break? Now you understand why it breaks much better, because it's your thing. You created it and you made a change and you broke it deliberately. Therefore, now you have a much better chance of understanding what's going on, rather than if you take someone else's program or in a textbook and say, well, if you change this, this is going to happen. But it's someone else's program. You're not going to be as invested in it as if it was yours. And I think maybe that's a psychology behind why we understand things later in many of the complex stuff. Great. We can start talking about data representation now. This is the last class on data representation, and unfortunately, because of this Flex Day thing, we lost the Tuesday class. But I'm hoping that you would have read like Jaden, right, and got at least a passing familiarity with all the different concepts. But if you do have any particular difficulties with specific things in the area of data representation, you should bring it up now. And what we can do is, yes, Juan, yes.
I'm having trouble when you're doing scientific notation. I get the mantis, but figuring out the exponent.
Sure, great. We can. Thank you for asking, Juan. So I'm going to make a note of that. We've got at least one now. So we'll look at floating point notation and actually work through an example in class. Hey, Juan, does anybody, but especially if would be good if it was Juan himself, do you have access to to some kind of a tablet or an iPad where you can draw and share that screen? You do?
Yeah. I wouldn't be able to share the screen right now because I'm on my computer, but I do.
No, what you can do is you can log into Zoom on your iPad also, and then it gives you a second Zoom panel here.
Okay.
Is that a yeah? And then that you should be able to share. And are you going to use your finger, or do you have a stylus or pencil?
I have a stylus.
Great, fantastic. Okay, so what we can do is work through an actual example, and what we'll do I think this is a good idea. What we'll do is do scientific notation base 10 first, and then say this is base 10, and let's try and do the same thing in base 2. It's binary, and you'll see it's exactly the same. Is that useful for everyone? Because it is a hard. What Juan just said is actually one of the more challenging ideas to grasp in data representation, because floating point notation is not, completely obvious how it works, and scientific notation kind of directly leads into floating point notation. So we can talk about that. It's very nice. Anything else? So we have one thing that we can talk about today, and we have a whole 2 hours, right? So we have a lot of things we could potentially cover. So we have floating point. Any other difficulties you guys are having?
Just kind of a bit of confusion dealing with negative numbers.
Sure. Okay. Floating point, negative numbers. What else?
Choose complement.
Musa? Sorry?
Choose
Musa,
complement.
Choose complement. Okay. So these are really the three most challenging things that every quarter students always ask for. So yeah. So we can do choose complement, and in fact they're all. What we'll do is deal with Jaden's question first, because negative is the easiest. And then we can do a choose complement, and finally floating point. How about that? Does that work for everybody? Yeah? Okay, great. Hey, Jaden, do you actually for negative, we don't need a iPad or things like that. We can just talk and it'll make perfect sense. Yeah. So I can explain how negative, the negative number thing works with binary, and then we can take it from there.
Yeah, yeah, that's fine. I just always have notes ready to write down just in case.
Yeah,
if I need it, like if I need an example, like during the quiz, I just want to make sure I have a part ready.
Yeah, don't worry. And by the way, even if you don't take notes or forget to take notes, you can always ask again in the subreddit, saying, hey, we talked about this in the lecture, but I'm not really clear. And then someone will respond, or I will respond, and then you have your free notes right there online. So you can just print it out, or it'll be right there in front of you. Okay, so there you go. So I think, well, why don't we do these three concepts, and then at the end, if we have time, I think we'll have time, we can talk about more things too. Negatives are an interesting thing, right? Because with numbers, as you know, with binary, we only have a way, or even tally marks, right? We only have a way of representing non-negative numbers. And again, I want to make this, even though I myself make this error many times, saying negative and positive, negative and positive. That's just because I'm, used to human speech, right? With humans, when we're talking to humans, we say negative, positive, and we think that all the numbers are covered there. No, so positive does not include 0, and negative does not include 0. So if you want to cover all numbers, we got to say negative and non-negative. So non-negative includes a 0. So it's not symmetric though. It's not symmetric because you got non-negative has one extra symbol than all the negatives. Yes, because non-negatives has a 0 and then 1, 2, 3, 4, 5, right? But the negatives doesn't have a 0. It starts at -1. Does that make sense? So and it's kind of interesting because that means with tally marks and everything, we can represent all the non-negative numbers, but we cannot represent negative numbers, and especially when it comes to bits and bytes, because when it comes to representing the numbers using electronic means, by the way, it does not have to be electronics, right? We are using electronics and electrons and currents, electric currents, because it's just fast, but you don't need electricity to build a computer. You can actually build a computer out of water pipes too. You just need the analog of a transistor that is mechanical. It's just going to be very, very slow. So given that, we say that if you want to represent ones and zeros, we want something in the electrical world that gives us two different states. So if you have a pipe that conducts water flowing through a pipe, you can have two states. Either there's water flowing through the pipe or no water, it's empty. Yes, either or if you have two cups, a cup that's full and a cup that's empty, assuming you can't have half full and up, right? So you have two states. So that's 1 and that's 0, a switch, up, down. So you only have two states that you can distinguish visually, or tactile, or you touch it and there's current flowing in there and so on. So there's only two. So with these two states, you have binary, and we want to be able to say, well, you know what, I want to have negative numbers, so there's a negative sign. But the negative sign is actually a dash. It's not a 1 or a 0, it's a dash, right? So how do you represent the negative sign? There is no switch. You can't, if you think of the bit as up and down for 1 and 0, you can't leave it in the middle and say that's a negative sign, right? So because you only have current flowing or not flowing. So how do we represent negative numbers? By the way, before we start talking about that, how many possible numbers, how many possible bit patterns can you represent using, let's say, I shouldn't say n, let's say 4 bits, okay? If I give you 4 symbols, okay, 4 bits, that can be 1 0, that can be 1 0, that can be 1 0, and that can be 1 0, okay? So how many possible combinations of 1 zeros can you get with 4 bits?
16.
16, thank you, Xiangwan. So it's 16 because it's 2 to the 4. And in module 0, I actually walked through an example in English, why it is 16, why it is always 2 to the power. Because every time you get one more, and I think we talked about this before, maybe I talked about this as 2C students, every bit basically doubles the amount of space you have. And so if you start with only 1 bit, you have 1 and 0. But if you had one more bit, then that bit can also be 1 and 0. Yes. So for that 1, you have a 1 and 0. For that 0, you have a 1 and 0. So essentially, you have 2 of these, and 2 of these is 2 times 2. That's 4. Yes. And if you add one more bit, for each one of those values, 1 and 0, you have 4 here. So it's 4 times 2 again. 4, right? So if you have 3 bits, it's 2 to the 3. If you have n bits, it's 2 to the n. Yes, so that is the basic thing that we all have to be 100% comfortable with. So if you have n bits, the total number of distinct pictures you can create. Picture, it's essentially a picture. Right? A pattern is a picture, isn't it? If you have n bits, the total number of bit patterns you can create out of that is 2 to the n. Now, if I have 2 to the n bit patterns in a sequence of bits, and so I can say I have a choice. I can either represent 2 to the n non-negative numbers. All of them I use for non-negative numbers. In other words, all zeros is actually 0. All zeros and then a 1, which is a different pattern, I'm going to say that's a 1. So every one of the patterns, 2 to the n patterns, has a different positive number associated with it, and it's 0, of course, right? So you have 0, 1, 2, 3, all the way up to 2 to the n. So 2 to the n patterns, well, 2 to the n minus 1, basically because we included 0, right? So you have that many patterns, and all of them are being used to represent non-negative numbers. But I want negative numbers. What is a good trick? What can we do if we say that this is the way I'm going to represent my information, but I also want to represent negative numbers? What do you do? Is there an idea? Because it's a hack, right? It is a hack, and it's such a fundamental hack that was introduced into the very core of computer science that we don't even look at it as a hack anymore, right? Because we say, well, this is what we have. We have bits that can give you, tally marks essentially, in base 2, and I can represent all the non-negative numbers, but I want to represent negative numbers, so I need to hack it. I need to make some changes here so that I can represent negative numbers. Yes? How do you do that? Take a guess, okay? It's okay to be completely wrong. I want to keep saying that again and again in my class. It is okay to be completely wrong, because that is the only way we learn. Yeah. So if I want to represent negative numbers in using bit patterns, how would I do that?
I believe there were
Full of 1.
I'm sorry. Hey, Jaden, you cut out.
Sorry. I think someone was also. I think there was 2 ways: either sign magnitude or choose complement notation.
Yes, thank you. And actually, give me 1 sec, okay? I'm going to switch the audio from Alexa to this laptop because there's a lag and it's messing with me. Where's the speaker icon? Yeah, I put it on Alexa because it's a blare on the speaker of my Mac, and hopefully it shouldn't matter. All right, say something, Jaden.
Is it working now?
Actually, no. Oh, I need to change it in Zoom, not in Mac preferences. One sec, okay? In Zoom, speaker is not Alexa. Built-in speakers. Okay, built-in speakers. That should work. Yeah. Can you say something again, please?
Is it working now?
Yeah, it's working. Okay, it's going to be a little bit of a blare. I can live with it. Yeah. Okay. So what Jaden said are basically the 2 different hacks we've come up with. 2 different hacks that we've come. One says, I want to represent negative numbers and non-negative numbers. I'm going to take all the numbers that I want to represent. Let's say negative 7 or negative 8 to positive 7, right? That tells me that I have negative 8 to negative 1. That's eight patterns. Yes, negative 8 to positive 1. I want eight of my bit patterns reserved to represent negative numbers, negative 8 to negative 1. And I want another 8 bit patterns to represent the non-negative numbers, 0 through 7. This is crucial. Please stay in step with me. And if you are even the slightest bit confused, please let me know, okay? Please let me know. Hey, Nutnail and Sakshi and Juan Bello. Oh, we have 2. Oh, well, I see that this is you. All right. Okay. So please switch on your cameras if you're able to. Thank you very much. And that would be fantastic. All right. All right. So yeah, especially Nutnail, because you have all these colorful lights in the background. So all right. So
sorry, did you want me to turn it off? Was it bothering you?
No. It's actually very nice. Last class I was enjoying it. All the different colors.
Oh.
So
Okay.
thank you. All right. So so do you understand the hack here? We're saying that we have in 4 bits, 2 to the 6, 2 to the 4, 16 different bit patterns we have. We can create 16 distinct pictures. Okay. They have to be distinct. Basically, I give you a picture and say, what picture is this? And you say, hey, that picture is 4. That picture is 7. because they had to be different, right? Because if they're the same, you can't distinguish the numbers, right? So you have 16 different pictures using 4 bits. And of the 16, originally using, the only positives thing, we were good because your binary notation for 0 is the same as, is everything is your 1 in binary will be the 1 in your representation also. Everything will actually line up. In your binary number will be the same as your decimal number. That's basically it. The binary number will be the same as a decimal number if you're dealing only with only positives. However, we say that we want to use negatives. So we say we're going to take all of the bit patterns we have, chop it up, and say I'm going to use 8 of those bit patterns for my negatives and the other 8 for the non-negatives. Now, in order to do that, what we do in sign magnitude notation, the first hack is to say that, well, this bit pattern, which is 4 bits long, I'm going to imagine that it's not really 4 bits long. It's only 3 bits long. And this last bit, I'm going to use it to indicate the sign. It's positive or negative. So that means with 3 bits, I can have how many different values?
I believe 6 different values.
2 to the 8, right? 2 to the 3. 2 to the 3.
2 to 3.
Is 8. So essentially what we say is that bit is going to be my, 2 to the 8, 0 to 7, 0 to 7, yeah. Okay. 0, 1, 2, 3, 4, 5, 6, 7. That's 2 to the 3, 8 possible bit patterns in 3 bits. So we're going to say in sign magnitude notation, I'm going to take 1 bit off, and that bit is going to be my sign bit. If it's a 0, it's positive. If it's a 1, it's negative. So that is your sign magnitude notation, and that lets you store negative numbers also. Because if I want to store -7, I'm going to say 1 in my sign bit, which is going to be negative, which signals that it's negative. And then I'm going to store the 7 using 1, 1, 1, 4 plus 2 plus 1. We're using 3 other bits. Does it make sense?
So we use a 1 in this case as the negative sign?
Yes, we basically say that the leftmost, well, in this case, the left one of those bits, you can choose any bit, right? One of those bits, I'm not going to treat it as a digit. I'm just going to treat it as a negative sign. Either it's there or not. Essentially, you're taking a bit pattern and saying, I want to represent a number, but I can't use all of the bits. I'm going to use all of the bits except 1, because that 1 bit I'm going to use for a different thing, not a number, whether it's 0 or 1. So whether it's positive or negative, or negative or non-negative. Does that make sense? Right? This part, if you get past it, this basically sets the stage for also understanding 2's complement and everything.
Question, Professor?
Does it make sense?
No, Professor.
Yeah. Who's this?
No, it's Nate.
Nathaniel, yeah.
Yeah. So for the additional bit to indicate the magnitude, the direction, can we just like functionally speaking, like mathematically speaking, is it like multiplying by -1?
Nathaniel, can you give me 1 sec? I want to get my AirPods because my speaker blare is too much. I can't even hear you. Hang on.
Sorry.
Sorry about something, Professor. I need to have my video off for a
Hang
few
on
minutes.
1 second.
I'll be right here still listening to the lecture.
You guys can talk amongst yourself if you like. There's my speaker icon here. Oh yeah, I am connected to my. Yeah. Okay. Can you say something?
Yeah. So my question. Can you hear me, sir?
I'm sorry. Yeah. It says these things are need to be better interface. Okay. I need to change it in Mac as well, not in Zoom, not in Mac. Okay. All right. Now I'm connected to my AirPods. Hopefully. So yeah. Say something, Nathaniel.
Can you hear me, Professor?
Fantastic. That's great. By the way, how do you want to be called? Is it Nathaniel or do you have?
You can call me Nate. It's fine.
Nate. Okay, Nate is easier because it's only 1 syllable. Okay, go ahead.
My question was like functionally speaking, like if we were to write it down on a piece of paper mathematically, like that -1 would be the outsider, right? Like I'm multiplying all of the outcomes by -1, right? Or am I wrong?
if you write it on a piece of paper.
Right, like if we were writing it as some equation or a formula, like for every outcome for the entire outcome, that -1 would be the multiplier. Can we do that or not?
Oh, I see. I see. So basically, you want to split out the negative. No. The way you write it is basically, all right, here's what we do. I think this is a better way. You just write out the entire bit pattern, but the understanding to a person that you're giving that bit pattern is that this bit pattern is stored in sign magnitude notation. So there needs to be an understanding. If you put something together in sign magnitude notation and give it to someone and say, here is a number, but it's in 2's complement notation, then that number is totally gone. Right, it's screwed up because it's a different notation. Yeah, because they take two languages that use the same script. Like the many languages in Europe use the same script, right? The Roman script. So you can write something in English, but it won't make sense in French. So 2's complement and sign magnitude are two different ways of representing negative numbers. So both the writer and the reader need to know what the language is. Otherwise, they'll get confused. Yeah, does it make sense? So when you write it down, you basically write out the entire pattern and say, this is sign magnitude notation, and you have the sign bit and the rest of it is the actual value. So this is a sign and this is the magnitude. That's why it's called a sign magnitude notation. And so it's a wasteful notation because it has two different representations for 0. Because 0, it doesn't make sense to have -0 and +0, right? There's only one 0. So, but in sign magnitude notation, there's 2 zeros. You have and you can already tell that in the C++ programmers absolutely would hate that because we're after every single bit, every single electron. So but it does have its place. The 2's complement is slightly more sophisticated and it actually works. And in order to see how 2's complement works, all we're saying is that, well, I don't want to use 2 patterns for 0. Now, hey, the first question I hope we've addressed, Jade, with the negative numbers and the sign magnitude notation. So we're going to talk about the 2's complement notation now, which I believe, who was Nate? Did you ask about 2's complement? Someone asked about 2's complement. Who asked about 2's complement? No, we don't need to talk about 2's complement.
Oh, that was me.
Musa, yes, okay. All right, so in 2's complement notation, we say we have 8 possible patterns and we want to be able to represent both negative and positive numbers. So what we'll do is essentially create a number such that if you add this to the original number, you get all zeros for the bits that you're interested in, while being cognizant of the fact that when you add these two things together, you may get all zeros, but you may have a carry. You may have a carry on the leftmost side that doesn't fit into the bit pattern, has to be discarded. Does it make sense? So we can work through an example. We can work through an example on a piece of paper. In fact, what we'll do is if you can share your iPad screen now, what we'll do is work through an example in base 10 to say this is how we represent a negative number in base 10, not binary with bits. Okay, if we do the base 10 negative number, so it's going to be 10's complement. It's not 2's complement, it's going to be 10's complement. But 10's complement, 2's complement doesn't matter. It's all the same. The principle behind it is the same. So 10's complement. So let's take a 3-digit number. Okay, 3-digit number. Yeah, let's take let's say we have 3 digits. Okay, let's say we have 3 digits, and so draw a box with 3 cells in it. Okay, 3 cells. Yeah, thanks. All right, so 3 cells, and so those are the cells. Those are the only cells we have to put our numbers in. And let's say we want to represent the number. So what is the maximum number you can represent? If you didn't have negatives, at all, what is the maximum number you can represent? We're talking about decimals, okay? Not even binary. This is Social Security. Yeah, go ahead. Just someone tell me what's the maximum number you can write in there.
I was going to say 256, but
no, not binary, not binary.
No, binary.
9.
Yeah, Social Security.
9.
999.
999. Yes, 999. So in 3 boxes, how many possible not bit patterns, digit patterns can you get? How many possible number patterns can you get with these 3 boxes? Yes, Nate.
So we, if repetition is allowed, it's going to be a 9 permutation plus 8 permutation plus 7 permutation, or
No. Actually, no, it wouldn't be permutation here because
choose. Okay.
yeah, because you can replace this, right? So
Right.
each of those cells can have 10 possible values, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Someone was going to answer.
1,000.
1,000. Thank you, Sean. Hey, how do you pronounce your name? Sean Wen?
Wen.
When? You just want to say one?
Chung Wen.
Sean Wen. I'll say
Yeah.
Sean Wen. Okay. All right. So 1,000. And 1,000 is because we have 3 digits. Okay. And each digit can have 10 possible values. So it's 10 to the 0, 10 to the 1, 10 to, right? So 10 to the 3, basically. So you have 10 to the 3 is 1,000. So you can have 1,000 different bit patterns here. So now we'll make a compromise and say that, well, you know what, if I use that to represent only negative, if I want to represent all numbers up to 1,000, right, 999, then I cannot represent negative numbers because all of my patterns are used up for just the positive numbers. So far, are we okay? Yeah. So we'll make a compromise and say, because I want negative numbers, I'm going to sacrifice half the space. I'm going to say that the first 500 bit patterns will represent negative numbers, and the next 500 bit patterns will represent non-negative numbers or something like that. How do we do that? So one way to do this is this clever technique. The 2's complement is not intuitive, but once you look at it in base 10, it makes total sense. Okay, so let's say, can you represent let's say negative 510 in what is called 10's complement, negative 510 using these 3 boxes?
No, you cannot.
You cannot, right? Because you can only have 500 non-negative numbers, but 510 is greater than, right? Yes, so you can't do that. So what we want to do here is essentially say, well, I can represent 0, negative 499, negative 500 to positive 499. That's my 1,000 patterns. So those are numbers I'm going to represent. Now, how am I going to do that? So we will construct this way, and let's say we want to represent negative 237. Okay, is that okay? We're just pulling a number out of thin air. So I want to represent negative 237. All right, negative 237, and put a negative sign in front. Right, a negative sign in front. However, we don't have something to slot the negative sign in. So what we want to do is construct another number under the box. Say x, and we want to calculate. We want to say x. We want to find out what the digits are. What we want to find out what the 3 x's are, so that if you add these 2 numbers, negative 237 and this number, actually, that's make the top one positive 237 and put the negative sign below for the x's, because the x is going to be this is our negative one, right? So put the negative sign below. Yeah. Thank you. Put the negative sign. Yeah, there you go. So, right. So now we want to add these 2, and below so if you add a positive number and a negative number, what should you get? Positive 237 and negative 237. If you add them 2, what should you get? 0. Yes. Thank you, Nate. Okay. So we need to get all zeros at the bottom. Right under the line, write 3 zeros. So that's what we want, right? If we add those 2 numbers together, right? Maybe the notation. Let's refine the notation a little bit. We're not subtracting, because technically subtracting is the same as adding the negative value. Yeah. So, but in order to make plus, and you want to put a negative sign somewhere in there. Yeah. Okay. All right. I think that works. Okay. So we want to say 237 plus this number, which we're going to create, should give us all zeros, and only for the 3 bits. Okay. So in other words, we don't care if adding these 2 numbers gives you all zeros, and then you get a carry. So what happens if you add 237 and let's see, what's 1,000 minus 237, by the way? It's going to be 763. 763? This is 763? I think so. All right. So what happens if you add 237 and 763? You get 1, 0, 0, 0, right? 3 zeros and then a 1 on the left. And that 1 on the left is a carry, because you add the leftmost 2 digits, you get a 10, and you write the 0 and carry the 1. But there's no box to put the 1 in, because you only have 3 boxes. Yes. So that 1, which was a carry from the leftmost bit basically fell out of the boxes. You can't represent it anymore. So you're going to discard it. So you discard the carry, and now we've come up with a crazy way, a crazy way of creating a negative number, which is really not a negative number in our usual sense of the word, but we've created a bit pattern such that if you add it to the positive value, a positive version of the same bit pattern, you get all zeros and there. So how do you get that? How do you find the value of x, and x? In fact, let's call them x1, x2, x3. So that we want to find the value of x1, x2, and x3. How can we find the values of the 3 digits, x1, x2, and x3? 763, and that'll give you all one. No, go ahead. Go on, complete that. If you add those two together, you're going to get 1,000, right? Put the line, you get 1,000. Is everybody okay with this so far? Right? I want all of us to be on the same on the same page. Yes or no?
Just to confirm, so as long as we have 3 zeros at the end of the number, then we have the right digits?
As long as we have 3 zeros, I missed the last thing you said. We have what?
We have the right digit. Like as long as the multiplication.
Yes, you're right, Shadi. You're right. As long as we get 3 zeros there, that is good enough for us. There's not a question of right or wrong, because what we're trying to do here is we're coming up with a bit pattern that is good enough to work in the context of negative numbers and does everything we want negative numbers to do. It's just a bit pattern that behaves like a negative number. It's not a negative number, right? It's a bit pattern that behaves like a negative number in every possible way we can think of. So we're coming up with a bit pattern. So how do we come up with this is 763 and we get the 1,000, right? So now we want to calculate the values of this is 763. All right, I'll show you how to get there. Okay, so 237, 1,000 is nothing but 999 plus 1. Yes, it's 9,999 plus 1. So we start with 237 and find a number which, if you add to 237, will give you all 9s. That's the first step. Yes. So let's do that. So 237, what can you add to 237 so that you get all 9s at the bottom? Thank you, Juan. Right. So he's actually thinking one step ahead and doing these things, and I'm absolutely grateful for that. Okay, so we want to say, what do you and what should and don't write anything, Juan. So someone else, right? Tell me what should be under the 2 so that when you add these two numbers, you're going to get 999. What should be under the 2?
762.
Yes, there is a 7. What was it again?
762.
Oh, I see. Oh, you told us, yeah, the whole number. Yes, 762. Yes, thank you. Shadi said the whole number. I was expecting just the first one. Right. So if you do that, you get 999. Yes. Now we're there, almost. Okay, we're almost there. Now the number that Shadi has created. Am I pronouncing your name right, Shadi?
Yes. Yeah.
Shadi. All right. So the number that she has created is basically what is called 9's complement. Okay, it's not 10's complement, it is 9's complement. This complement is basically what's left over after you've taken something out, right? In geometry, you have these angles, right? A complement of an angle and so on and so forth. So that's the 9's complement. However, we want the 10's complement because, if you use the 9's complement, that's not going to give us our so that's not going to give us a negative number. So when you add it, you're not going to get zeros. You're going to get 999. That's not negative. So we want to add one more to it. Okay. Once you add one more to that bit pattern that Shadi came up with, we get 763. Yes. Now, if you take the 9's complement and add 1, you get the 10's complement. And that number you can use as the negative of the first number for all practical purposes, where you have a limited number of boxes to put your digits in. Does that make sense? Okay, this is a very crucial point. And if you're comfortable with this, you'll be totally comfortable with 2's complement. Yes or no, right?
Sorry, can I ask something?
Yeah, please do. Hey, Juan, your palette and the pencil thing is, or you can scroll it up. Scroll up it's hiding. Yeah. Thank you.
Yeah.
All right. So go
sorry,
ahead,
I just
Jaden.
yeah, I wanted to ask. So, in this case, does that discarded one act like as the same as a sign notation? The one becomes
No.
like a
Good question. And thank you for asking that, Jaden. Right? No, the discarded one is discarded. You don't care. That's gone. Okay, it's gone because now the only bit pattern we're interested in is 763. Because 763 I can treat as the negative of 237. If I only had 3 boxes, I can treat the 763 as the negative of 237, because if I add those two together, I'm going to get 1000, which is all zeros, and the 1 will be tossed away. So for all practical purposes, I can treat the 763 as a negative, even though it is not negative 237. You can look at it and say it's not negative 237. Yes, it's some other number. But we're going to say we'll pretend it's negative 237 and it works for us. Yeah, it's getting our mind around that is hard. Okay, because we're staring at an obviously positive number, 763, and we're saying we're going to treat that number as a negative number. It's negative 237 because if I add it to negative 237, I get all zeros and the 1 that is going to be carried over and tossed. Is that okay? All right. So that is the basis of 2's complement. Now we have come up with a way in which we can create negative numbers using just the boxes we have and the symbols we have. We're not introducing a new symbol for a dash. That's the crucial thing, right? We cannot have, hey, Michael, you have your hand raised. Yes?
Yeah.
I'll come to you in a sec, okay? As soon as I finish up with Jaden, right? So we don't have an extra symbol. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We don't have the negative sign. Yes?
Yeah. So, sorry, what I'm kind of getting is the positive 763 acts as the negative 237.
Yes. In fact, we are assuming we will treat positive 763 as negative 237. That's what we're saying. We're saying, hey, you are positive 763, but I'm going to treat you as negative 237 because when I add you to positive 237, I get zeros. So even though our eyes lie to us, right? We look at the number and say, that's not negative 237, that's 763. You say, no, that's actually negative 237 because I only have 3 boxes to put in. And in 10's complement notation, that's negative 2. Yeah, it takes a little while to get used to it. Okay, but that is the underlying principle. And I just want you to be comfortable with this, right? Because, once you're comfortable with it and you get used to it, the understanding will naturally follow, right? And obviously, if you don't understand it, you can always, ask again in the Reddit forums. And we'll talk about it. We won't be able to talk about it in class because we have a lot of material to cover just in programming. So this is the last class on data representation. However, right, this is core to the understanding of all computer science. Therefore, if you don't understand anything with data representation, no matter, even if it's week 5, week 7, week 11, right, you should feel free to ask questions about data representation in the forums. And we will answer them. We'll people, your classmates, me, your tutors, we will all try and help you understand these basic issues because they're, key to understanding the rest of computer science. So this is unintuitive. That's why we're spending so much time on this, because we look at it, especially beginners, and say, that is a positive number, 763. How could it possibly be negative 237? This is how it can be negative 237. Is that okay? Yeah, Michael, you had a question.
Yeah. Is there an advantage of using this complement as opposed to the magnitude?
Yes, there is absolutely an advantage. Okay. Now I'm going to mention a couple of advantages, but there are many more advantages, and you can look them up. So the first advantage, obviously, is that it's not wasteful. Sign magnitude is wasteful, right? It wastes 1 bit pattern. There's 2 possible representations for 0. Yes, so it's wasteful. The second is that with 2's complement notation, and I don't want to go into the detail here because we don't have time, but you learn this if you do CS10 computer architecture, right? In computer architecture, they go into this in detail. I think I haven't looked at the syllabus for that class, but I'm pretty sure they'll teach it here. There. So what was I saying? Oh geez, I forgot. Hey, Michael, can you repeat your question again?
The advantage of
the advantage. Okay, right. So what happens is that if we represent numbers in 2's complement, a lot of arithmetic operations become very simple, right? Especially, adding, subtracting two numbers. If you take subtracting two numbers, you don't have, think about it. If you're in kindergarten, when we learned how to add and subtract numbers, are the procedures for adding and subtracting different or the same? On a notebook as a kid, as you were trying to learn, right? Where the procedures for adding and subtracting, they're different, right? Different algorithms altogether. Because in adding, you got to do carry and things like that. In subtracting, you got to borrow, right? So two different algorithms altogether. So if you had to implement that in computer science, there's two different algorithms for the basic arithmetic operations. But in 2's complement, if you use 2's complement, it's already simple right there, because you don't have two different algorithms. They're both additions. If you want to add, if you want to take 237 minus another number, all you need to do is 237 plus the negative of that number. So there's only addition. So already it's simpler, isn't it? So there's only addition there. And it's not just that. There are many other arithmetic operations also get hugely simpler, and also not just simpler, it's hugely more efficient computationally. There's fewer cycles that you need to put in and for calculations. So there's a whole bunch of advantages for 2's complement notation. And that is the reason why we use 2's complement notation. Despite there are so many different notations for representing negative numbers, we use 2's complement because it has so many advantages, both computationally in terms of efficiency, as well as, well, actually representationally, right? Representationally, it's not wasteful. So there's two advantages, okay? But you can actually go to Google or even Wikipedia and look at negative representing how different ways. You can say advantages of 2's complement, right? You can actually ask Google too, right? Say what are the advantages of 2's complement notation, and it'll come up with the whole page. I'm pretty sure, right? There's so many different things you can do in 2's complement that are so much easier and simpler. Does that make sense? Now that we've mastered 10's complement, I can show you how to do exactly the same thing in 2's complement. Okay, is that okay? Are we ready to move on to 2's complement now? Yes or no? You have to be interactive, okay? All of you have to be interactive and talking, because otherwise, if I'm the only one talking, I don't know if you guys are understanding this or not. Okay, so please be vocal and talk, right? Like Jaden and Michael and Nate, they're the only three people who have talked. Oh, Xiangwen also talked. So and Musa. All right, I can see more of you talking, right? But please be more vocal. And so we want to do 2's complement. Are you ready to actually do a 2's complement conversion right on screen here? Yes or no?
Yes.
Yes,
Thank you. All right, so let's be very simple here and just do 4 bits. Okay, 4 bits like we talked about before. Okay, 4 bits. Yeah, thank you, Jaden. That's 4 boxes, and here we don't have. Oh, by the way, here's a trick. Okay, that I do when I have to chop it up into 4 boxes. What I tend to do is first chop it up into 2 equal boxes, and then 2 equal boxes I chop it up into 2. And this trick I learned when I was cutting cake for my daughter's birthday one time, a long time ago. So if you keep cutting slices, the slices get smaller and smaller with more people coming in. But if you cut it in half, and that way it works. Okay, all right. So with 4 bits, you can represent 16 possible patterns. Yes. So you can go from technically you can go from 0 to 15, or you can go from negative 16 to positive 15. Hey, negative 8 to positive 7. Negative 8 to positive 7. Yes, they're both 15 different numbers. Negative 8 to positive 15 numbers. So what we want to do, which means that the maximum number you can represent, maximum positive number you can represent in 2's complement has got to be 7 or less. So far, are we okay? Because we can't represent 8. Yes, we can't represent 8 here because we chose 2's complement with 4 bits. We are coming in with the compromise and the understanding that we cannot store numbers bigger than 7 because half of the space, 0 to 7, that's the only space that's available for positive numbers. The rest of it is for non-negative numbers. The rest of it is for negative numbers. Yes. So if I said this 4 bits represent the number 9 using 4 bits in 2's complement, you'd have to say immediately, no, that's not possible. In fact, that would maybe a question in your midterm. No, I can't do data representation questions in the midterm, I think, because there's too many other things to do. But this could potentially be a question in the data representation quiz, right? How do you represent the number 9 in 2's complement notation using 4 bits? Okay, and the answer would be, the correct answer would be, what would be the correct answer? If if you multiple choice, what would be the correct answer there? You want to represent the number 9, positive 9, right? In 2's complement notation using 4 bits. What would be the answer?
You can't.
You can. Thank you. Thank you. Jose, was it you?
1, yeah.
Who said that?
It was
Who said
1.
that, by the way? Oh, yeah, Juan. Thank you. Right. So you can. So because we've given it up, we said, I can't do it. I'm going to make a compromise so that I can't go all the way to 15. I'm just going to stop at 7 because the other bit patterns are from a negative. Okay. So now let's say I want to represent the number -6. Okay. -6 is possible, isn't it? Because my bit patterns in 2's complement will range from what is it? No, it's going to range from -8 to +7. Okay, so -6 is in that range. -8, -7, -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8. No, 7. Right. So those are the numbers we can represent. So -6 is in there. We can represent -6. So let's try and find out the 2's complement representation of -6 using 4 bits. Are we okay with this? Do you want to do this or not? So raise your hand or say yes or no if you want to do it, because if you already know how to do this, we won't do it. Okay. Okay, so let's do it. Okay, so at least some of you want to do it. Let's do it. Okay, so let's start with, so in order to do that, we're going to start with +6, and let's write the binary representation of +6 right there. Right? What is the binary representation of +6? Binary representation of +6. 6 is what? What is 6? 6 is 4 plus 2. You just have to break it down into powers of 2. Right? 6 is 4 plus 2. 2 to the 1 plus 2 to the 2 to the 1 plus 2 to the 2. Yes? 2 to the 1 plus 2 to the 2 is 6, isn't it? 2 to the 2 is 4. 2 to the 1 is 2. 4 plus 2 is 6. Yes or no? So who one's written there is 0, 1, 1, 0, which is basically +6. You can write equals +6 on the right hand side of the box. Yeah, equals +6. Right? And you can put a plus sign in front so that it's very clear. Right now we want to discover what -6 is going to be. So we're going to do the same thing as before. So put the 4 boxes underneath and say, B1, B2, B3, B4. Those are the 4 bits we want to discover, right? B1, B2, B3, B4. We want to discover the values of those bits so that and say B1, B2. Yeah, thank you. And then write B1, B2, B3. Oh yeah, okay, that's fine. Right, and then you can say equals negative. You can say equals -6, just like that. You said for the equals +6, you can say equals -6. Right. So we want to discover what goes inside those boxes. So in order to discover what goes inside those boxes, we're going to do exactly the same thing we did in base 10. Okay. Now, would someone else like to do this, or would you like me to walk you through this? I would ideally like not Juan. Okay. I would ideally like someone else to talk Juan through what should go in these boxes, okay? Because that way everybody will be on board, engaged, and also understand it. So can someone volunteer? Or if nobody volunteers or nobody knows how to do it, I can do it. But I'll walk you through the steps too, right? So what we want to do is in those 4 boxes, we want to stick. Basically, let's do you can do the whole thing, right? We want to discover what goes in those boxes and think about what we did for base 10. What did we do for base 10? In order to discover the negative number, what did we do?
Was it for 2's complement? It would have to be like numbers that either change it to where all 4 boxes are filled up by 1s or 0s.
Yes. Well, you're very close, very close. You're getting to the right answer. So what? We'll take one more. Okay, we'll take one more student who can take a guess now, and then I can show you how to do this. Okay, can someone take a guess again? Another guess, maybe. So what we want to do is we want to derive the -6 bit pattern and think about what we did in for 237, -237. Okay, or whatever it is, right? So the steps involved. What was the first step? The first step there was getting all 9s. Yes. So here it's base 2, not base 10. So what should the first step give us? When you add those 2 numbers, the first step, what should it give us?
Should all be equal to 2?
Well, there's no 2 in binary.
1.
Oh, okay.
Yes, 1. Because, you know, think about it, in decimal, we didn't put all 10s, we put all 9s. Yes.
Yeah.
So it's 1 less than the base. So we want a number that if you add to 0, 1, 1, 0, gives you all ones, 1, 1, 1, 1. Yes or no?
Yes.
Great. Okay. So let's say that in those boxes on the top where you have -6, we're going to say, we're going to put digits in there such that if you add them all, you get 1, 1, 1, 1 at the bottom. So say, oh, actually, for now, let's erase the equals 0 because we want to do the ones complement first. Okay. So now in the boxes, put in numbers such that if you add those two, you're going to get 1, 1, 1, 1. So put 1, 1, 1, 1 in the bottom also, right? So now is everybody okay so far? If you add those two numbers, you get 1, 1, 1, 1. Yes or no?
Yes.
Great. So this number is called the ones complement. Okay, just like in the 237 case, the first number we got was called the tens complement. It was the nines complement. The first number we got was nines complement. Now this is the tens complement. This is a ones complement. Ones complement. Okay. Now what do we do after that? What do we do after that?
We add 1.
We add 1. Okay, exactly. All right. So you add 1 to that bit pattern, that 1, 0, 0, 1, 1, 0, 0, 1. If you add 1 to that, then if you add that number to that, you would get all zeros and the 1 carried over. Yes or no? So let's try that. Let's try that now. So what do you get if you add 1 to 1, 0, 0, 1? What do you get if you add 1 to 1, 0, 0, 1?
You get 1, 0, 1, 0.
Thank you, Hyungwon. Right? So you get 1, 0, 1, 0. Is everybody okay with this so far? Right? Just counting in binary. Adding 1 to 1, 0, 0, 1 gives you 1, 0, 1, 0. Yes? So now we're going to say, we're going to try it out. Let's try it out before we say, oh, we got the big pattern 1, 0, 1, 0. That's the two's complement of -6. Before we go boldly out there saying that's your -6, let's test it out. Make sure that it actually works. Okay. So let's add those two numbers together and make sure we get all zeros. Okay. So let's write the first bit pattern. I think it was 0, 1, 1, 0, and then add the other one. Yeah, +6. And now we'll add the bit pattern. That's 1 added to that one's complement. Hyungwon, what was it? 1, 0, 1, 0? No, I forgot what you said.
1, 0.
Yeah.
1,
Okay,
1, 0. Yeah.
Is that right?
Yes.
Yeah, I think so. All right. Now, if you add those two together, let's do the addition just like we do in kindergarten. Okay. So take the rightmost digit, and 0 plus 0 is 0. So we can put a 0 under that. Right. And then the next one is 1 plus 1. 1 plus 1 in binary is what?
0 and carry 1.
Yeah. 1, 1, 0. Someone said, Tim, did you say 1, 0?
Nate
I
said
said 0 and carry 1.
Oh, yeah. Okay. Yeah. Nate. Yeah, thank you. So, Tim was trying to speak, but Nate was speaking. So I latched on
Right
the
behind
wrong panel. All right.
Sorry,
Sorry. All right, cool. So, right. So 0, and then they carry the 1. Now 1 and 1 again, 0 carry the 1, 0 carry the 1. Right? So you can put a 0 there in the leftmost box also, and you still got a 1 carry, and that 1 is discarded. Now you see how that bit pattern that we just constructed functions in a way that is satisfactory for us to treat it like -6 in binary. Because when you add it to the +6, you get all zeros. Yes? That's great. That's great.
So,
and it's this. Sorry. Yeah. Go ahead.
So the negative variation binary would be. Oh,
1,
sorry.
0,
Never
1,
mind.
0.
Yeah. Okay.
1, 0, 1, 0 is -6. We understand, or basically we not understand. We accept, or no. What is the? It's an agreement, right? We say that we will assume that 1, 0, 1, 0 is a bit pattern in 4 bits representing -6 in 2's complement. Because if you add it to the +6, you get all zeros. You're going to get that one that is going to be discarded by the hardware, because you only have 4 places to put it. When you add it, you get zeros, and 1 is discarded. Yeah. So you get 0. It behaves like a -6, so we're going to treat it as -6. Even though it doesn't look like -6, it behaves like -6. So we're going to treat it as -6. Yeah, so that's why it's not intuitive. Does that make sense? Okay, great. I'm happy to see that. So that is our -6, and that is how you convert a number from positive to negative. And the cool thing about 2's complement that I really like is that it, and most people even don't realize this, even though they may have gone ahead and understood more advanced concepts in computer science, they've missed out this part, which really, I think, is that the whole idea behind this concept of 2's complement demonstrates one of the most striking features of the computational way of thinking, or a scientific way of thinking about this, because we took a limitation. Think about it. It's a limit. The fact that you can only store 4 bits is actually a limitation, isn't it? Because in true binary, just like in true decimal, there's no overflow, right? You can add any number to any number, you get another big ass number. Yes? In true binary, there's no overflow at all. There's just numbers. So, but then we say, well, we can't do true binary because we don't have infinite space. We only have 4 bits. Okay, what can you do within the constraints of the 4 bits? So it's a limitation. Yes, it's a limitation, isn't it? If you only have 4 bits. Now, the genius here is that we took that limitation that we only have 4 bits and turned it around into an advantage. Because of that limitation, we now have a way to represent negative numbers also in a good way. Okay, so that is a incredible, isn't it? That aspect of development in computer science is missed by many people, because it's actually a stroke of genius to say that take this limitation and turn it around and make it an advantage for us. So even though computers only give you, a limited space to store numbers, like, they come in packs, 8 packs, right? A byte is 8 bits. We say this limitation of 8 bits is going to turn out to be our advantage, because we can use that limitation to manufacture negative numbers such that when you add it to another 8-bit number, it'll result in a 9-bit number where 1 bit is that carry and everything else is 0. So we can treat that as a negative number. So we turned it around and turned a limitation into an advantage and leveraged that. And that is the genius of 2's complement notation. And it takes a little while to I think, appreciate that, because many times people only appreciate things after we've run into difficulties, or there's a saying, isn't it? You don't realize how good it is until it's gone, right? So so many times we know how to do this, but until you run into places where you're not using it and run into a problem and say, wow, 2's complement actually helps me here, right? Then you start appreciating it, because you say, oh, I had a limitation, but that limitation has become an advantage now because I use 2's complement. And it's not just 2's complement. As you study computer science, you will see many algorithms, many techniques that were essentially just limitations turned around into solving a difficult problem. Because we take a problem and try to fit it into a limited space where the correct part falls into the space that you have and the incorrect part is discarded. There are many algorithms that work like that, so that you take the limitation and make that your advantage. And that's, I think that's a good paradigm to exploit in many cases. Is everybody okay with 2's complement now? If everybody's okay with 2's complement and you can do your own conversions, we can go on to talk about what was the next thing? A floating point notation. Who asked about floating point notation, by the way? Someone asked. Oh yeah. Go on. So we can talk about floating point notation, scientific notation and floating point notation. Everybody okay with this now? Okay. Right. So here is the fundamental idea behind floating point notation, right? So let's say you wanted to add 2 numbers. Let's say you want to add 3.14, 3.14. Let's say 3.14 plus. Well, actually, let's write 2 numbers in. Let's write the numbers using scientific notation, right? 3.14 times 10 to the 0. That's pi, right? Our approximate value of pi. Say 3.14 times 10 to the 0. Right? And we want to add that plus, and let's say plus plus
Put the
42
plus
times.
at the bottom or like next to it.
Yeah, however, yeah, whatever you like. I think we'll play with it later. Yeah, right. So plus, let's say 6.5 times 10 to the 3. Right. So how do you add these two numbers together? If I gave you those two numbers, how would you add them? Yes, Nate.
We have to change their power. We have to put them to the same 10 to the power of 3 or 10 to the power of 0, both of them.
Yes.
So
thank you.
we will add 6.5 times 1000 plus 3.14, or 3.14 times 10 to the power of 3 plus 6.5 times 10 to the power.
No, you can't. No, you can't do 3.14 times 10 to the 3. That changes the value.
Oh, I'm sorry. I mean increasing their power and moving the digit. I'm sorry.
Yeah.
Yeah.
I know that's what you were trying to say. Yeah. All right. Okay. All right. So is everybody okay with what he said? Hey, Shadi, you raise your hand. You have a question?
No, I didn't raise my hand.
All right. Okay. Everybody okay with this? I can see all of you, by the way, because the screen. Oh, actually, I can fit more of you on screen. Wait a sec. Okay, got more of you now. Is everybody okay? Raise your hand if you have a question or if you don't understand. But otherwise, I can we can proceed. Okay. So what Nate said essentially was that we can't add those two because the powers are different. It's like saying what is ax plus by? You can't add ax plus by. It's got to be ax plus by. But you can add ax plus bx. Yes. Because you can factor out the x and you say ax plus bx is x times a plus b. Yes or no? Yeah. In fact, you can even write that out as an example. You cannot add ax plus bx, ax plus by, but you can add ax plus by is just ax plus by, but ax plus bx equals x times a plus b. Equals, you can't change that. However, ax plus bx can be rewritten. Could be equals x times a plus b. Is everybody okay with this? It's algebra, isn't it? Right? It's basic algebra. So is everybody okay with this? So now we have 3.14 times some number, 6.5 times another number. We want to get at least one of those numbers the same. Obviously, we can't change the 3.14 because then the value will change. The one thing we can change is the 10 to the thing. Yeah. So we can rewrite 3.14. Or let's rewrite the other one. It's easier. Okay, like Nate said. So we can rewrite the 6.5 times 10 to the 3 as another number times 10 to the 0. So what would 6.5 times 10 to the 3 be if you wrote it as some number times 10 to the 0? Equals what? Right. One is waiting for you to say. Yeah.
6,500.
6,500 times 10 to the 0. Yes, thank you, Nate. Okay, and also I want other people than Nate to also participate. Okay, some of you are participating, I think, but some of you are quiet, and I'd like all of you to participate. Okay, Jason, who else? Hasanta, I think Sakshi, Yu Young, Kiki, right? Kiki.
Yes.
Kiki's Delivery Service, the Miyazaki film, it always comes to mind. All right, and then Mia, and all of you should also feel free to speak up. Okay, just keep talking, and it doesn't matter. It's the computer science. Learning any subject really grows through conversation rather than through some person just talking on and on. Because if I'm just talking on and on, you can switch me off mentally. Even if you're looking at the screen, you can switch me off. You can be thinking about something else. However, if you're also participating, you cannot switch me off, because then your mind will be in a different gear altogether, because you'll be interactive. Be interactive, because that is the easiest way to learn. If you're not interactive, you can still learn, but it'll be hard. Because if you're not interactive, you're saying, I'm going to try and learn the subject using 10% of my cycles, or 10 cylinders, or 2 cylinders of the 6 cylinders firing in my mind, right? However, if you're interactive, you will actually learn with all 6 cylinders firing, because you're on the edge of the seat all the time. And you're going to say, I got to be on top of it. I got to be on top of it. You're always there. Okay. And then if you don't understand something, you'll always say, no, can you please go back? I need to get that. Right. So be interactive. That's the best friend you have to learn any subject, not just computer science. Right. So is everybody okay now? 6.6500 times 10 to the 0. And actually, who wants gone one step further, and he's actually taken the dot and put it at the end. Right. So he's put the dot there. I didn't have, I wasn't thinking about, I wasn't planning to do that, but he's actually done that, which is cool, right? So we put the dot there because the dot is implicit, isn't it? Every number you write, there's a dot at the end. If there's no dot inside, there's a dot at the end. 0.000. Yes? Okay, so he just put the dot there. And there's a reason why he put it there. It's because it says the point hasn't vanished. It is just floated over from here to here. Yes? That's by changing the exponent, we took the point and floated it to the end. It didn't vanish. It's there. It's there, right? Okay. Now that we have the dots in the same place, now we can line up the dots and add them because the exponents are the same. Because now we can say that this is basically 10 to the 0 times 6500 plus 3.14. Yes, we can rewrite that as 10 to the equals 10 to the 0 times equals 10 to the 0 times. Thanks. Yeah, 10 to the 0. Yeah, times, and then 3.14 plus 6.5. Yeah, oh, it's 6500. Right now we get the answer. Right now we can get the answer because it's 6503.14. We can do the addition, right? And we can do the addition only because the exponents are the same. Now, this is the only insight that we need to get solid on in order to understand floating point notation, because that's floating point notation in base 10, right? People always say floating point in base 2, right? You're trying to understand two things at the same time. You're trying to understand binary, base 2, as well as floating point. No, it's never the way to learn any subject, right? And I know from experience that when there's a lot of things to be learned, if I try to learn two things at the same time, it is far less efficient for me. So what I try to do when I have to learn many things is that I try and break it down. I say, do I need to know this before I know that? No. Okay, so I'm not going to learn the two together. I learn this and then go there. That's always the easiest thing to do. So here, what we've done is basically saying, I want to learn floating point and binary. So let me not worry about binary because I'm still new to binary. I learn about floating point with what I already know, which is base 10. Decimal numbers that I work with every day. Now I know how floating point works in decimal. Yes, is everybody clear on how floating point works in decimal? And it's called floating point because the point basically floats to the end when you adjust the exponent. Yes?
Yeah.
So that's why it's floating point. Now you can get the answer. Now in base 2, you do exactly the same. In binary, you do exactly the same. If you want to represent a number, what we say is that I have 8 bits to represent a number. And in my 8 bits, I'm going to chop up the 8 bits. Technically, in practice, really, right? Real floating point numbers are not 8-bit, right? Real floating point numbers are like 4 bits, or I think a floating point number in C++ is 4 bytes. That's 32 bits long, right? But we're doing 8 bits just for pedagogical purposes, just to get the idea across, right? So if you have 8 bits, we're going to say I want to represent both the mantissa, which is the 6.5, and the exponent, which is 6.5 times 10 to the 3. So I have 2 numbers to represent my actual value. I have 6.5 and the 3. Yes? With those 2 numbers, I can reconstruct my 6,500. Yes? If I got 6.5 and 3, using those 2 numbers, I can reconstruct 6,500 anytime. So now all I need for floating point representation in binary is basically 2 chunks of just bit streams, right? So 1 bit pattern to store the 6,500, another bit pattern to store the 3. They're both numbers, and there's no special symbols here. There's no dot. I say because in binary you can't go and put a dot in there. Well, in binary you can, but you can't go inside a computer and put a dot in there because then a computer only has 2 switches, up and down, 0 and 1 and 0. There's no dot or a negative sign. So that's why we have all these contrived and clever ways of representing things that require symbols that are beyond 1s and 0s. So here, what we want to say is, well, I'm going to use 3 of those bits to store, and you can divide it up with a vertical line. and say, yeah, those 3 bits are going to be my exponent, and the remaining 5 bits are going to be my mantissa. Now, how many bits for the exponent and how many bits for the mantissa? Well, we're just picking it arbitrarily here, right? Just for illustrational purposes. However, in actual practice, you have 32 bits for floating point numbers, right? Floating point numbers are in 32 bits. And I don't know, you can look it up on Google, but I think what they do is of the 32 bits, they probably use 25 bits for the mantissa, and they use the remaining, I don't know, 7 bits. No, I think it's more than that. Yeah, maybe they use 12 bits or something for the exponent, the exponent, and then this for the mantissa. So you can split it up in different ways, and that division is actually the result of some calculation that showed this is the most efficient division of, because looking at data and how the patterns of how people store numbers, this is the most likely ranges that would work. And so people split up the 32 bits into the exponent part and the mantissa part. So when you store a number in floating point notation, it is actually stored as 2 different numbers in a single bit pattern. Okay, in one single bit pattern, it stores 2 numbers in 2 different parts in floating point notation. One of them is the exponent and the other is the mantissa. Is that okay so far? Okay, so that's all we have to understand when we need to do floating point notation, because we say that when we have 2 numbers and we need to add 2 floating point numbers together, we cannot add them if the exponent parts are different. So what we need to do is essentially turn the mantissa into something else such that the exponents are the same. That's all we're going to do. So if we had, let's say, let's try and do 6 times 2 is 12. 6 times 4, 24. Yeah, let's try 24. So if I said 24 in 24, and 24 would be 6 times 2 to the 2 to the 2. 6 times 2 to the 2, right? So write 6 in the mantissa in binary. That would be 0, 0, 1, 1, 0. Yes? Yeah. Oh, yeah. 0 and then 1, 1, 0, 0. Yeah, that would be 6, right? So you can say that's equal to 6, and the exponent we would say, let's say, and then the exponent, let's say, is 4. This is 0, 1. Yeah, 0, 1, 0. No, 1, 0, 0. 1, 0, 0. Okay, now equals 4. Now, and then this whole number together is going to be 6 times 4 equals 24. That's your floating point number. Yes? However, we made a small compromise here, right? Not compromise, one small fix. We need to make one small fix to get to where we are. If you notice, what we did here for the exponent was basically assume that the exponent is always going to be positive or non-negative. We didn't allow for the exponent to be negative, but exponents can be negative, right? You can have 2 to the negative 1, 2 to the negative 1, 2 to the negative 3. Yeah, so the exponents can be negative too. Matrices can be negative. So both of those chunks need to be either 2's complement or sign magnitude notation. They both need to be capable of representing negative numbers. Yes or no? So if we use a 3-bit exponent, we couldn't store 2 to the 4. Yes? Because 4 is not possible to represent in 3 bits. Therefore, in realistic situations, the exponent is actually big enough so that you can actually put a 2's complement negative numbers in there. So you can put the value negative 300. Wow, can you represent negative 2? I don't know. So you can put a negative value in there. Okay, it says it's stored in 2's complement notation. Is it stored in 2's complement notation? We have to look it up, right? The exponent is stored in some notation which allows for you to store negative values, either 2's complement or sign magnitude, right? I think it's 2's complement. You can look it up, right? So the exponent is a number and the mantissa is a number. When you want to add 2 floating point numbers together, the process to add these 2 floating point numbers is not the same as the regular addition process, right? Because in school, we learn when you add numbers, you just line up and add it up, right? So, but it's the same algorithm, borrow and everything, as long as the thing is But here, what we have to do in floating point addition is if you say add these two numbers and their floating point, the computer has to use a completely different algorithm to add two floating point numbers. And that algorithm is going to take the exponents and make sure the exponents are the same, and then add up the 2-bit patterns. Right? And in order to, so let's say that instead of, how else can we represent this with, let's say 12, yeah, 12 times 2, right? So another way of representing 24 would be 12 times 2. What is 12? 8 plus 4. So that would be 0, 1, 1, 0. Yeah? 8. So you can create 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0. Oh, yeah, 0, 1, 1, 0, 0, is it? Yeah, 0, 1, 1, 0, 0. That is your 12. 0, 1, 1, 0, 0. That is 12, isn't it? Because it's 2 to the 3 plus 2 to the 2 to the 3 plus 2 to the 2. 8 plus 4 is 12. Yes, equals 12. Now, 12 times 2 is also 24. So let's say your exponent is 2 here in 3 bits. That would be 0, 1, 0. Right? Now, if you wanted to add this number to that, we can, because the exponents are different. So the way we would do that is say, well, we can't, the 24 we want is not this 24, but that 24, right? So that is how we change the exponent and we turn one number into the other. Now here, notice something really cool, okay? Notice something really, really cool here. And I think this, and it'll also help. In the process of turning that number into this, what we did was basically took a 2 out of the exponent and multiplied that into the mantissa. Yes? We had 6. We took a 2 out and made that a 12. 6 times 2. And so we can reduce the exponent by 1. Yes or no? Yes?
Would an easy way to imagine this would be moving one of those zeros at the back end of 6 all the way to the front?
No. Actually, you're asking exactly the right question. The perfect question to ask at this time. Thank you, Jaden. Okay. So Jaden is asking, how do you go from this to this, right? And there's actually a really cool way to do it. And in fact, what Jaden observed was almost correct. Okay. So what Jaden said was take that 0 and stick it here. Basically rotate everything and you get 6 to 12. That's what you said, Jaden. Yes? Right?
Yeah, that's
almost right. Almost right. Except it looks like rotation because the 0 came in. But it's not rotation. It's actually shifting out. So the whole pattern moves to the left, and the leftmost 0 is gone. And this hole, the brand new hole that was created, is 0, right? Everything that's coming in comes in as a 0. So that's called a left shift. It's a left shift operator. Every time you multiply a bit pattern by 2, all of the numbers move to the left by 1 space. And this is not unintuitive at all. Think about how you do it in decimal. If I gave you a number like 237 in 4 boxes, 0, 2, 3, 7, and I said, multiply that by 10, what do you get? 2, 3, 7, 0. The 2, 3, 7 move over here and a 0 is added at the end. Anytime you multiply any number by its base, the whole number shifts 1 step to the left. And the converse also holds true. Anytime you take a number and divide it by the base, the whole number will shift. If you take, 2,307 and divide it by 10, right? Let's have a 0 for the 2,370, right? And divide it by 10, the 0 basically shifts out, right? And you get 237. So shifting to the right is the same as dividing by the base. Shifting to the left is the same as multiplying by the base. Are we comfortable with that? And that's the exact same thing that happens in base 2. And I used to say this in my previous classes. Anytime we are stuck with a problem in binary, okay, binary arithmetic problem, the trick is not to panic, and the trick is basically to say, all right, I don't know how to do it in binary, but I know how to do it in decimal because I've been doing that ever since kindergarten. So let me just forget about binary and think about how to do it in decimal. I'm going to do exactly the same thing in binary. It'll work. Okay, so that's what we've been doing all class today. Yes. Whole class, we're doing something in decimal and showing that the same thing works in binary. And in fact, exactly the same thing will also work in base 27. We do the names, multiply by 27, everything gets shifted. All the letters will get shifted one step to the. You can try it out, right? It's going to be painful, but you can try it out. So in base 27, any base it'll work. Base 8, base 16. If you multiply by the base and divide by the base, it's the same as left shifting and right shifting. And this is so cool, really cool, because if you think about it, multiplication, addition, subtraction, they're all very expensive operations. Well, not very expensive. They're relatively expensive operations when it comes to the CPU. Because adding two numbers, right, or multiply, you've got a whole bunch of things happening, right? You got carry, borrow, and all those things. Yeah, a number of operations happening. It's not like two instructions. For the CPU, it's not like, like that. When you add two numbers, it's got to do a process like we do on a piece of paper. Yes? And multiplication is just repeated addition. And so you can already imagine, if you want to do multiplication, there's going to be a process that's going to be harder. It's going to take more time. Maybe instead of 10 instructions, it'll take 15 instructions, whatever, right? However, multiplying and dividing by the base is a super cheap, and in fact, one of the cheapest instructions the CPU can ever execute, because it is just a shift. There's no sophisticated algorithm there. Anytime you say multiply by the base, right, it is the same as left shifting. I'll say, I'll take that bit and copy it over here. This bit, copy it over here. Well, actually, let's start here because it doesn't want to override anything, right? It'll say, I'm going to shift this bit out, and this guy goes here, this guy. So it's basically like, Hilbert's Infinite Hotel, right? You know about Hilbert's Infinite Hotel, right? So you have the whole hotel is full, and one person comes in. They create a room for that person by saying, everybody move to the next room, right? It's still an infinite number of rooms, and you can fit that person in. So you have this bit pattern, and you want to shift everything out. You take the leftmost guy and toss him out, right? And move everybody else one step to the right. And you get a hole. And that's your new bit, right? So that's left shifting and right shifting. And it exactly works like you would do in decimal. Now, is that okay? That is basically how two's complement and a floating point notation works. We won't go into the details of actually working out the sum of the mantissa and some of these things. All we need to know is basically what happens. Because once you know what happens, right? The first thing I need to do in floating point is make sure the exponents are the same, right? And making sure the exponents are the same is exactly the same as what you do in kindergarten and on a piece of paper, where you line up the dots, right? When you add two numbers, you line up the points, right? And then you add the numbers, yes or no? That's what we do on a piece of paper. So making sure the exponents are the same is basically the electronic way, the computational way of doing exactly the same thing. Making sure the exponents are the same is lining up the dots. And then you do the addition in the usual way. It works. Obviously, usual way meaning you have to add the exponent separately, and you don't even have to add the exponent separately. The exponent is factored out. So the exponent is the same. The mantissa needs to be added in the usual way. Yeah? No, is that clear for everybody? Does everybody still have any lingering doubts about these representations? We actually managed to cover the whole thing. I was pessimistic when I started this class, thinking, well, I used to talk about data representation for 2 classes, and now I only have 1 class. How the hell am I going to do it? But I think we covered everything, starting from binary representation all the way through to floating point, which is really the hardest. But if you're solid on floating point, you're solid on data representation, I think, right? Everything else is easy. ASCII and all, they're just representations, easy to understand. Floating point is the hardest concept to understand in data representation. If you understand how it works, basically the principle behind it, lining up the dots and then adding the mantissas, right? And the exponent is the same because it's factored out. Yeah. So is everybody okay with this so far? Thank you. Right. If anybody has any questions, you should feel free to ask. We're at 9:34. We still have approximately a half hour. So what we can do now is I can basically just stick around, and you guys can talk amongst yourself, and I can be here for help. If any of you want me to pull me in and say, hey, what should we do here? I'm happy to come and jump in and help out. But what would be really nice is if you guys can basically talk amongst yourself, and hopefully Juan will continue to manage the whiteboard. And thank you, Juan. Right. So if you guys want to try something on your own, say, hey, Juan, let's try this. And let's say, Shadi says, oh, I have this number. I want to try and convert that from base 16 to base 2. We won't do that. Okay. Yeah, sorry.
I have
Go
a
ahead.
quick, or anyone really, is there like a resource that you would recommend so we can practice some of this, so we can like just kind of keep practicing it on our own?
Yeah. Did you have module 0? Did you read module 0? By the way?
Yeah, I read module 0 as
So I
well.
thought I might have mentioned a few problems here and there in module 0.
Yeah, you have. I was wondering if
You
there's
want extra
anything
resources?
else, just in case. I don't know.
What I would do is just go to Google and
Okay.
say sample problems for sample problems binary to decimal, or sample
Okay.
problems floating point conversion. Just pick out the keywords.
Okay.
It's like a ton of sites. Okay, there's a ton
Okay.
of sites out there, like the questioning system, leak code, and things like that. They're to do with programming, but I'm pretty sure there's a ton of sites for dealing with numbers, because there's so many people teaching math and these things, right? Discrete math, and they probably have sites that let you go there and interactively try things out.
Awesome. Thank you.
Jose, if you find those sites, can you also share them? And they were very,
Yeah, we'll do.
yeah, it'll help me also, because I can
Yeah.
point other students at it.
Yeah, I'll make sure to put it in the Reddit.
Yeah, what we want are sites where you can go, it'll just give you a problem and you have to solve it, and then it'll tell you, well, this is the correct answer and this is how I got it, right? There's a lot of sites like that, and it'll be very instructive. And in fact, if Jose comes up with some sites, I might actually integrate that into module 0 if I can locate the source file for that. I think it's in a Google Doc somewhere, right? This is like, so many years since 7 or 8 years since I wrote it. But I'll insert those links. I'll locate the file, insert the links, and republish it so that it'll be useful for everyone. Thanks. Anything else? Or are you guys happy to talk amongst yourself? In fact, what I can do is, what I usually do is, if there's a professor staring at you in your face, people are usually reluctant to talk and converse. So what I did in the past was, I'm here, okay? I'm going to be behind the screen. I'll be walking around, maybe. I'll be here. I'll have my AirPods on. I'll be listening to you guys. But I'll turn the laptop around to, look at the yard or something like that, so that I'm not in your face, which I think has helped free up people before. So they feel more free to talk amongst each other. Okay, just be mindful that it's going to be recorded and it'll be on YouTube for students who are absent, and pass this message on, right? Being absent in class is a sure way not to, make it all the way to the top grades. And being present in class is not only useful to pick up the material, but also to get participation points. Okay, but still, if you do have to miss class, and you can send me an email and get points back for it. But for those people, these recordings will help. So it's being recorded. So feel free to be your, I'll tell you what is going to be really useful and what is, in terms of video, right? In terms of your video presence online in public, this is what is going to be really useful to you in public in the future. And other people looking at these videos, trying to identify strong hires for their companies, right? These are the qualities they look for. They are not looking for wise guys. They're not looking for know-it-alls. They're not looking for people that are boastful and saying, I know this, it was all easy for me. Okay, they're looking for people who are curious and genuinely interested in learning something, even if it's something basic, right? Even if it's something basic, if you ask questions and say, well, how do you do this? How do you do this? Like many of the questions we had today, not all of them were basic questions, but even if they were basic questions, it is actually, I'm very happy that people ask that, because it shows that in order to understand that, I need to understand the basics first. Let me make sure I have that, right? Because a lot of people would say, I'm too scared to ask the basic questions. I just assume that I'll pick it up on my own. I'll learn this. Bad strategy, okay? Because then they're setting themselves up for failure. It's much harder, 10 times harder to learn the advanced stuff if you don't have the basic stuff in place. So why would people punish themselves? Many people punish themselves by going to the advanced stuff before mastering the basic stuff, right? And I know, because many people come to community colleges and say, well, you know what, I don't really have to study hard in community colleges. I'll just pick up a piece of paper and then go on to some other college where I'll do a master's and learn the real stuff. They're going to fail. Okay, you'll never pass your master's if you don't master the basic material. So this is the place where you need to focus more, because if you focus more on the basics, you don't have to focus as much in the advanced stuff. And so feel free to be your curious, inquisitive stuff, no matter how basic the material is. Because if I see someone on a video that is curious like a child, okay, trying to ask questions, and try to figure out. And even if they're puzzled and saying, you know, rubbing their heads and saying, oh, I'm trying, how does it work? Okay, that kind of person, people follow. Okay, they'll say, all right, let me look for more videos in this of this person. And if they've gone from here to here, okay, maybe this is not the end of the world. Maybe that's not the, you know, the goal, but they've gone from here to here. And how did they go? They asked questions. They were curious. They were really genuinely interested in wanting to know. That's the person I want in my company, right? Even if it's entry level or, you know, whatever it is, I want that person. Because that person can be groomed. That person can be groomed eventually in 20 years to become the CEO even, right? Because that's how they do it, right? You take all the big companies, CEOs, the greatest job of a CEO is not to run the company. The greatest job of a CEO is to identify and find the next CEO, right? Because, you know, if they say that I've got this great company and it's fantastic, but after I'm dead, this company is going to go to the dogs, that's not a good CEO, right? Because any great CEO has a vision that spans longer than their own lives, millions, you know, thousands of years even. So they're going to say, well, after I'm done, who's going to lead the ship? I need to. So they're going to be thinking and looking from day one. As soon as they get into the CEO hot seat, they're going to be looking at everybody in the company, right? Meetings, all hands. They're going to be looking at people and saying, who is this person? I want to see if that person can be given more opportunities to grow. And eventually, you know, come and relieve me, right? So I can go off. So that's what everybody's looking for. So be your inquisitive self that wants to learn things, and you'll just go on and on to the top of the world. Okay. So I'm going to turn the laptop around. You got 20 minutes now. Please feel free to converse amongst yourself. Try to come up with your own problems, right? And maybe someone could say, hey, Juan, can we do this? I want to try and convert this number, or I want to add these two numbers. Can we try one more 2's complement example? Okay. Can we try a 10's complement example, and so on? Do all of that, right? Experiment and find out. The only way to learn computer science is by practice and getting familiar, right? Like Einstein said, you know, von Neumann said to Einstein, getting familiar, getting used to it is the most important part. And initially, it is going to look completely foreign to you. For many people, right? Except for the people who already know a bit of programming, this will look completely foreign. Because it's a new language, isn't it? Not just C++. Even all of this is new language, the manipulation and everything, new way of doing things. So it's going to be confusing. And for many nights in a row, you're going to go to bed having accomplished nothing, or thinking you have accomplished nothing. But I told students last class, the optional class, it is not like that. Okay. We think we've learned nothing, but you don't know, right? You don't know that you have learned a lot, because in your brain, some rewirings have happened because of what you've seen, and you can't perceive that, right? Those rewirings need to just grow, and at some point it'll become what is called an epiphany, right? So people think when they have epiphanies, wow, I just got this idea out of the blue, bam, I hit it, right? So, but that's not it, right? Many times epiphanies are like mushrooms, right? How, you know, you go into your yard on one day, and all of a sudden you see like 100 mushrooms, bam, like that. And they're all grown in a circle, like in a pattern or something like that. And you say, how could it happen overnight? No, it didn't happen overnight. These mushrooms have been growing for a month, right? And they came up because it was flowering season, or one day. I say, now the time is right to release our pods and the seeds. So like that, epiphanies happen like that. So we think that, you know, oh, this happened one day, bam, like that. No, it's lots of little things, little rewirings in your brain. And finally, that final piece falls into place in the jigsaw puzzle, and you can see the whole picture. And we set ourselves up for many, many beautiful epiphanies in our lives by persevering and saying that I'm going to keep going, even though I think that I didn't learn anything. I'm going to go and do it anyway. Because at the end of 10 days, you'll see that, well, it wasn't nothing. Every single day I actually learned something, because otherwise I would never have learned this now, right? Because, you know, you look at it every day and, you know, I couldn't have learned it today. I couldn't have learned it today, but in the 10th day I learned it. So I couldn't have learned it all on the 10th day. So you must have learned a little bit of it all along, but you didn't know, right? So just keep that in mind. It has worked for me, saying that even if something looks formidable and impossible to master, just keep at it with time and perseverance and patience. It'll just happen for you, right? And and you'll see, right? You'll see. If it doesn't happen like that, let me know, right? I won't say this again in future to future students, but nobody has told me or disproved me so far. So so I'm happy to see all of you guys, right? And like this, right? Always keep your cameras on, because your beautiful faces should be on YouTube, right? And I'm happy to see this. You're all engaged. Thank you, Juan, for taking the screen and doing this today. Last class I had Chaitra, Juan today, and hopefully more people will also volunteer. From Tuesday onwards, we won't require an iPad, mostly. Sometimes maybe we'll use an iPad, but Tuesday onwards will be coding, and we'll use an IDE or even an online IDE initially, right, to start coding. And again, when we start coding, what we'll do is essentially we'll pick up a screen like this, share your screen. We'll go to a private tab in your Chrome or Safari window, Edge window or something like that. And it has to be private, okay? Because the reason I say it has to be a private tab is because if it's not private, you may accidentally expose your password, or I don't know, your history. And a lot of people, even if they look at your browsing history, they can find out a lot of personal detail about you, and it's risky. So make sure before you share your screen, it's a private tab. And you share a private tab, and then I'll take over from there, right? Or one of the students, and we'll say, all right, on the tab, go to this URL, and then here we can start editing your code, and I'll call out the code letter by letter, right? And again, in the past, people have found that initially they're waiting for me to speak out each letter before they type it, C space, and so on and so forth. But before you know it, you'll be typing ahead, okay? And that will happen even without you knowing. And you can watch these videos later, right? You can come back to your videos and watch videos of you coding, and you coding initially when you had to wait for me, and then 10 videos later you're not even waiting for me, right? I'm up here and you're already down there and coding. So you can see all that, and it's actually very nice, and very nice to see your own progress in the rearview mirror. So so you can set yourself up for that, and it'll be a very nice experience. Is that okay? Are you all happy and happy with the class? Was this class useful? Did you guys learn something useful today? Yeah. All right. I'm glad to hear that. Musa and Hasanta, I didn't see you guys. Good or not? Musa, are you here? Are you on a bus? No. Okay. Good. Good. All right. So yeah, thumbs up if you got something useful and will help you for your data representation quiz. It's due tomorrow. Okay. Data representation quiz due tomorrow. Start today. Let's start today. And how long is it? I don't think it's a fixed time. You got 18 hours. Okay, you got 18 hours to finish the data representation quiz. So you can start today and finish it tomorrow. And even after you start your data representation quiz, if you got stuck on a problem, don't answer it wrong. You can leave that window, go to Reddit, and say, "Hey, I'm trying to solve a problem in data representation, and I have this. Can someone help me?" Someone will help you. And then you can take that answer and put it in your data representation quiz and you can pass, right? Well, not pass, you get more points, right? So you can do all that. It's 18 hours long. That if it's not 18 hours, let me know. I'll change it, okay? The data representation quiz should be a long time format quiz, so that you get an opportunity to work things out and ask people.
I don't think it was 18 hours.
Oh, it wasn't?
No, it was
Okay.
only 2 hours, I think.
I see. I'll change it, okay?
Yeah,
I'll
so-
change it. I'll change it later today. I'll make it 18 hours so that you can interact with your fellow classmates before you answer questions. Okay. But the most important thing is do everything on your own. Okay. Even if someone else gives you the answer, try and figure it out before you type it in. That way, it will make it easier for you downstream. Okay. I'm not saying you have to do this because it's the right thing to do. That's total bullshit. Okay. I'm saying you have to do this because your own life is going to be so much easier. Just in a few weeks' time, if you master all this, you'll find it easier. Actually, I shouldn't say a few weeks. It should be when you start doing 2B and 2C. All of this will, being masters of data representation is going to be so much easier. And the other thing that I said in the previous class that is missing here is that every quest that you complete in CS2A, all of the blue quests, 9 blue quests, get started on them as soon as possible. Every one of those quests will give you points for CS2A. Those quests give you points for CS2B also, right? You get grade points for blue quests in CS2B. They're not new blue quests. If you solve them now, you can get the same points in 2B and also in 2C. Well, only my sections at the moment, because other instructors probably don't honor this. But if you do my sections of 2B and 2C, you get credit for blue quests in 2B. You get credit for blue and green quests in 2C, right? It's a significant number of points, actually, right? It can make a difference in your grade. So, and on the negative side, people who didn't do the quests and get into 2B, they still have to do all the blue quests in order to get those points, all right? So they have to do double work. So do all the blue quests now and finish them up. So when you come to 2B, you're already on a running start. You're up there when many of the new students are just starting here. And you're very close to, not very close to completion, but you have very high chance of completing it successfully and getting a good grade. Right. So thank you all so much. I actually totally enjoyed this class. Okay. Even though it was completely extempore and, Juan just picked up the screen and also partly it was because Juan was thinking ahead and doing a lot of my work, right? By lining things up and, many things that I would say we have to do. He's already done on the iPad screen. So that was very helpful. And that's part of the reason why we managed to cover all the material, I think, so quickly. So thank you all. I hope to see you all on Tuesday, right? And in the meanwhile, if you have any questions, and if there's more than 5 of you at any time who want a special class on a subject, on a topic, just let me know and find a time, right? Even if it's a Saturday or Sunday, I don't care. As long as I'm not doing something already, I'll just fit it in and I'll give you a class, okay? And because at the end of this class, what I want, my goal is for you to complete all of the class, be on top of the material so that you will all go on to do my 2B, right? Which is more challenging, a lot more challenging than 2A, but you won't feel it's challenging at all. If you've completed 2A successfully, 2B will not be challenging. It'll be easy. And all these other people will say 2B is a really challenging course, it's really hard. Oh my gosh, I'm sorry for you because you enrolled in Anand's 2B, right? Right? Because those people find it challenging. But people who do the 2B, they won't find it challenging at all. It'll be easy for them. So please do this. And likewise, even after you finish my 2C, people will say, oh my gosh, if you want to work at these companies like Microsoft or Google or Facebook, you have these problems, you don't even understand the problem in the first place. How are you going to craft a solution, right? But that's because these people haven't understood the fundamentals of algorithms, right? By the time you finish your 2C and you're solid on algorithms, you'll understand problems, okay? Understanding problems is the first step. Most people don't understand the problem. That's why they can't come up with a solution, right? You will be able to understand all the problems when you finish 2C, right? And then you'll also have a very good intuition of what solution to use, right? What tools to bring to bear from which part, okay? And so that your machine works. So because you know what the tools are. If you didn't know what the tools are, how are you going to build the machine? So 2A and 2B show you these are the tools available to you so that when you go to 2C, okay, well, I can put it together and I got it to work, right? But if you didn't know the tools, when you get to 2C, you're going, I don't know how to solve this, right? I need a particular kind of wrench. But is there such a wrench? I don't know, right? You got to go asking. But that wrench already exists. And you would have been told that in 2B and 2A. All right. So thank you all. We still have like 2 minutes of your time, but 5 minutes of your time. Talk amongst yourself. If you have time or people stick around, feel free to work through problems and call me. It doesn't matter if it runs over time for the recording. After you're done, the last person to go, just call me to stop the recording. Okay, I think it's recording now. Yes, it is. So stop the recording, and then I'll go ahead and see how to upload it to YouTube. All right. Thank you all. I'll see you on Tuesday. All right. Bye.
Thank you.
Thank you, Professor.
Bye.
Thank you.
Actually, Professor, can I ask something real quick?
Yeah, sure.
So the data representation quiz will ask questions about each notation, equation, and what was taught in basically the module.
Yes, only module 0.
Okay.
Data representation quiz is going to be like what we just did. You'll get 2 numbers, and then what's a sum, right? You get a floating point number. You might have a question saying, what is the mantissa? What is the exponent? Things like that. Yeah, basically just conversion problems like that. And you might get a number and say, you've got to convert from base 8 to base 2. Stuff like that. Okay. All right. See you guys later. Bye.
Thank you. Bye-bye.
Bye. Just call me, the last person to leave, just call me and I'll shut off the recording.
Yes. You can shut off the recording. Have a good day,
All right,
Professor.
thank you. I'll do that.